Okay. Little technical issue here. Something's went wrong with this. I put on OBS live, and now I'm wondering what's going to happen. There we are. Okay. Okay. Okay, so what we need to do here. Oh, I guess it doesn't show the properties in here. That's annoying. But what we're going to do is we're just going to add in the debug, we're just going to start with doing the 32-bit version of the code. So we're going to do that as fast as possible. Should be faster, but there is some different issues. So for the debug and release, we'll just copy the 64-bit debug release ML command. Except we take out ML64 and we change it to ML. Okay, and for now we're thinking about maybe just sharing the source code. So again, you can't see this properties window. You could share it, but it's something I seldom open right now. Though I mean, if we get intense into this, we may need it more and more. Is I make it an output for the list file, so it will actually do the process. Okay, so we're getting some compiler issues. Oh, this is too big. Okay, let's make this smaller. So basically the issue is that this is 64-bit code. So now the command line options look very similar. I don't know if we need to change anything. We'll find out. The other thing I can say is that we want to know the conditional compilation. And so we know that if it's 64, and as far as I know, there's _M_X64, and so we can detect the architecture at compile time. Some people have suggested using ifdef-rax for the RAX register, but it doesn't seem like as nice of a solution. Maybe it's considered to be more portable, but I think you're going to just, every platform have to solve what the compiler variables that are present for you are. So what we could do is something like this. And if. And so this should get rid of all the code. And now we're getting that a model directive must be present. So there's some differences in making code for 32 and 64 bits. So we do have to use the .model directive. And it's going to specify a memory model, which is going to be, and then a language type, and the stack option. It's mostly for stuff we're not even going to be using, so it's interesting, but it's going to basically, we can just do the simplest here. So else, now we're finally code does nothing. We could actually even just delete this because, yeah, we'll think about deleting that. So we could just say model flat and it should compile. Oh, dot. It has to precede the code directive. So the way to do that then is you just say if def m excuse me, and if we detect it's x86, we'd put the model first. We don't want to put it down here. So okay, see if that works. Uh-oh. Oh, it's MIX86. Intel or something. I don't know what the I is for, but okay. Huh? No, it's still not working. I mean, that works, but the question is, why can't we detect it? Oh, this is for CL. Oh, then I guess we can't detect it. Question is, does it still build for 64? No. Yeah, for some reason you can't use if and def here. I don't know, because it's weird. Rax is a register. It's not like a define. This is really just hacking MASM here. Anyways, that worked. So I guess we're going to use the if def rax paradigm. So now we can actually just start writing the code we need to write, like jump topo. This one's easy. You just change 1, 2, 3, 4, 5, 6, 7, 8. And if we look at the list file, whoa. If we look at the right list file, then we can see this is a B9. Okay, just to kind of document what's going on here. Again, it's the same, so not too surprisingly, we're getting the same thing. It's just B9 immediate 32. Okay. And we're going to still be using this stuff. The main problem we're going to run into is that let's see, we can make this wider. Yeah, there we go. So the main problem we're going to run into here is that not this kind of stuff. In fact, this we could easily macro in a certain way. We could find a way to just make macros to make all this code the same. But we can see even in the assembly language, the only difference is a prefix for the 64-bit. To have that 8-byte move versus a 4-byte move. The jump, I mean, yeah, it just uses EC. I mean, we can just macro the registers themselves. It should be fine, because macroing would do a copy and paste type operation. So what we're going to do here is we're going to continue, because we can actually do this kind of after the fact too, because we want to not play around too much until we know just what the details are going to be. So at this point, we know that, well, we know we don't even need this. So actually, one convenient thing, again, this is where the code paths are starting to diverge already. Because now we still, of course, want these meta tags in here, but things are going to be a bit different because, as we see, we're going to actually be able to not have to deal with all these stack alignment nuances in the 32-bit world, as far as I know. I mean, we can check that in the manual. Finally, we take the big function here, the blueprint, and then we actually have to just start, translating it line by line. Shouldn't take too long to do this. But there's going to be problems. Not here. Not here. Here we just kind of start slowly fixing this stuff up. But the problems are going to start occurring when we're using RIP relative addressing, because you don't get instruction pointer relative addressing. We don't need shadows. We don't need all this alignment. We can delete all these comments even for now. So 1, 2, 3, 4, 5, 6, 7, 8. These lines are fine. So far, so good. So far, so good. So far, so good. Absolute addressing now. Let's see here. Again, we can't use relative addressing. We have to use absolute addressing. The problem is then we need to know some of these absolute addresses. Now, we'd either have to relocate all of them when we build the blueprint, which would make the 32-bit model worse, actually, if you think about it. So this is kind of an annoyance. I mean, for now, we could just change it like this, but invariably, we know this isn't going to really work, so. Pop the EAX should be the same, I think, instruction, just in a different mode. Again, this is all going to be, you're just changing R to E, basically. The number one change everywhere. But there will be a little bit of bytecode changes. These, no. But this one, where these prefixes, mostly just with prefixes. That's it. As far as I can tell, there won't be much else besides the RIP relative addressing and the prefixes. And yes, calling back the lambda might have like a little bit of different semantics to it, but I don't think so. I think it'll still be the ECX and a call. So what we can just do is just start correcting things. And this is the best idea. Just quickly correct everything. Oh no, we don't need a shadow space. So there's certain aspects where this is getting actually better. It's improving. Actually, we need to fix these instructions too. Now this actually will be the same. But we're gonna need to like redefine a bunch of things here. Anyways, we're gonna slowly but surely do this. Actually, this isn't that slow right now. We're going at full speed ahead. So it won't compile, of course, if we don't fix a lot of this, so we will right up front. As I'm saying, mostly I'm just expecting that we're going to drop those prefix bytes when it comes to self-modifying code. So here we are. We're going to call the EAX now. But this -8 stuff we won't need either. There's going to be a bunch of simplifications here. Yeah, this is why it could take some time, because we have to think about some of these convenient simplifications going on here. So, okay, I mean, this is fine. I think this code is all the same regardless of the addressing mode. So far I don't see any issues with all that. Actually, this should be a B8. We should correct it for the other one too, but so far it's just a comment. It's a bad comment. So we changed from AX to CX. Alright. Again, I'm really tempted to just get rid of all of these load effective address ESP -8. We don't need to do any of this. We don't need this alignment, and we don't need a shadow space. In fact, things are about to get a lot simpler because of this, which is actually really convenient. We don't use Q-word pointers, we use D-word pointers. Okay. Just fly in here. Yeah, I probably have to just, mostly this is just going to be a debugging exercise and getting rid of all the special stack management that we had to do in the 64-bit. But then the key thing is going to be, how do we deal with the RIP relative stuff? How do we now make this code do some kind of relative type of thing? I mean, of course we could put the IP address in a register. We could even like pre-compute what we know the base of the function will be. But we need that function base somewhere. Probably the easy thing is to either put it in a register. You could also like call a fake function in return and use the stack pointer to access the IP address and just get the IP address. But I don't think that's a very nice solution. It's a possibility, but it's not a nice thing to be doing, basically. It's my opinion. Alright. Fortunately, we can get rid of all these things. I like that amount of this. And it's unclear how strict the 64-bit world really is with that alignment, but it does seem to suggest in the documentation it is. But I don't see any runtime stuff that really would mess up because of that, but could just be some processor optimizations or who knows why. It's recommended to do it that way. Okay, so again, if we just macroed the registers, it would actually take care of most of the changes that we've been making, and maybe macroing this -1. The problem is the self-modifying code itself is going to get a bit different, and we do have to be careful with that stuff. Okay, we don't need this anymore. I'm tempted to just get rid of all of it everywhere. I mean, technically we did the harder task first by doing the 64-bit variant. I'm sure I've not done justice to this yet, but it's close. Now it's very, very close to probably actually compiling. How many mistakes do I have in these comments and stuff? Okay, actually, this is where we can actually start deleting stuff. We don't need these -8 ESP stuff. None of it's necessary anymore. I mean, I'm hoping this makes things actually faster to get working. Okay. Nope. Don't need these. Okay, that's pretty cool because we've actually deleted a lot of code here. And, but unfortunately, every single one of these relative address scenarios is going to be a problem. I mean, we could either, relocate all of them in the blueprint. This one's already being relocated. Some of these are actually already going to be correct, but there's going to be problems here. We can actually just look at the file and start figuring out where the problems are going to be. Can see oh, we're in the wrong one. We can see the difference in the code. So we also see that even the offsets we're using are wrong. But yeah, we can see these are relative addresses, but you can't use relative addresses in 32-bit code because it assumes that it's going to be, the data is not going to be mixed in with the code, so they don't offer you this addressing mode. I'm like thinking about a register that we don't use. So we need to maybe check out the calling convention for x86. I believe it's going to be cdecal, caller cleanup, I guess. Which means we don't need to pop arguments off the stack. There could be some relevance to this when we call the lambda. Yeah, this is gonna be a little bit tricky. Ooh, yeah, this is gonna be. I think we don't have a choice but to relocate the whole thing because we can't really use a register because again, these nodes are changing which node it's at, so it would lose the context of the register. So, my feeling right now is the best thing to do is to use these relative addresses, but use them correctly. So we know that this is going to be always not -7 anymore, but this is -5 and -5. So yeah, okay. I mean, I admit this is tricky stuff. Did we screw up the 64-bit code and use 32-bit registers in here. Whoa. I'm just looking at this because I'm scared to change it without being ready to test it. But this looks like a bug. It should be RDX, obviously. Because Rax is going to be, yeah, it should be RDX. There's no doubt about it. That's a bug. This one isn't because we wanted only the CX, so that one's okay. Okay, so what about EX? Okay, so it was just one bug. Okay, good. So we don't use any 32-bit registers, I think, until we get to the 32-bit code. Okay, that's perfect. And we don't now have any comments about 64 either. So, okay, actually, we're well on the way to having a working code model here. So we need to fix a lot of these pointer offsets. I think we just have to kind of go one by one here and just decide what's going on. And then we're going to have to decide where the RIP relative addressing is just not going to work. Because these will be absolute addresses, which, of course, these like, there's very negative, negative 10 and positive 10 are going to be obviously invalid absolute addresses. And probably will just cause some kind of, segmentation fault type crash at runtime. So we don't need to make this so complicated, do we? This is now going to be a 0C3. Because we don't need the extra 8 bytes. I mean, I'm hoping, if I'm wrong about this, it would be having to fix everything just to change it back. So 1 plus 1 plus 8. Now, I think that's already been proven to be 1 plus 4 now. No, not here. 1 plus 4. So we can see that we can start changing these offsets. And then we also need to know, this would be a byte pointer. Okay, I'm okay with all these. It's just, unfortunately, we have all these extra relocations coming into the mix. I probably will have to make a big conditional compilation section for these things. Yeah, and we should regenerate the code just to fix that little detail about the RDX. Of course, it probably wouldn't matter. The graphs aren't going to be that large, but it's a bit sloppy to do something like that. So minus 1 plus 1 plus 4 plus 4. So this no longer is going to be 1 plus 1 plus 4 plus 4, but I don't know what it's going to be at the moment. So I'll take a look. And when I take a look here, I see it's going to be 1 plus 1 plus 4 plus 1. Okay. Again, all we know is we need to relocate all of these addresses. It's unfortunately making pre-processing work. However, that's it. I mean, it's still kind of O of N type of work. I mean, it's going to just do this in the pre-processing phase. A bunch of these metadata tags are still perfectly legit. However, they're not %2 anymore. They're all going to be %1 because remember, %2 was because of the prefix. So there's no more prefixes here. I'll tell you, there's some trickiness to all this. Again, anywhere we see these addresses, we know we want to define a macro. Unfortunately, that's going to need to be fixed up in some kind of code. We can probably use conditional compilation though to make the C code so beyond the blueprint definitions and these things, the rest will be just like a little extra snippet for these fix-ups in the 32-bit world. I think this is going to be a pretty nice way to go here. Wow. Yeah, I mean, all of these metadata. This is the tricky part about all this. And actually, the conditional compilation will make it, even trickier if we need to get comments correct, for the metadata, not to account for prefixes and stuff. This is going to really require stepping through the code and just finding out what's going on. It's a bit tricky to just say if any of this is going to work right off the bat. Again, putting these relative offsets is nice though, because we can just fix all of these fix-ups in one fell swoop. We don't need to do anything else. Theoretically speaking, this should be as simple as fixing up those things, making sure we've made the right code adjustments here, and it should just work. It should. We're not. Of course, we're not going to change the code model at all from what we have. We're going to leave everything. To be totally equivalent here. But it's easier said than done. Now this is where, of course, I know I need to do something immediately. It's like hardly a point in proceeding without fixing this. So we want to move. Again, this is going to be a fixed up address as well. I don't think we need this anymore either, fortunately. I mean, there's a lot of stuff being simplified here, which is great. Absolutely great to see that happening. Oh, these +1+1s are all going to be changing. I'll tell you, there's a lot of tricky things going on here. Ooh. Yeah, but the thing is, if we walk through each line of this once and the addresses are right, it's probably right. I mean, it's not like you have to do this again and again and again, but you do have to, do it once or twice and figure out what's going on. So what we need is to put this instruction in. And we need to find out what we're doing here. So we need to change a 58 to an 8B0424. One option is just to leave it here for the time being, because if we want to move on to other things, we can just leave that there. Yeah, I mean, it's the same without the prefix. As I say, everything is just prefixless now, because we can't move 3 bytes. Obviously, we'd have to do 2 in 1 or something like that. But what we can do is move a nop. So we can just peek anyways, it doesn't really hurt anything. And then we pop, or instead of popping, we nop. And this one's relative, so it'll work. Okay, so what does that look like? Does it look like it can do this? Or is ML going to make the same mistakes? No, ML works. It's only ML64. So, okay, that's good. Actually, that is kind of nice. I want to take a look at that compare instruction toward the bottom here. Make sure that that actually is going to work out. Let's see. Yeah, 2. As I mean, we're basically just subtracting 1 from everything. Okay, I mean, what we can do is we can get and do the first fix up. We can just make sure at least like we can still generate code and do some of these things. Yeah, let's actually see that that works. So the listing will be at this location. Yeah, it worked. Or, yeah, but perfectly. Worked perfectly. Yeah, I like what I see. I like what I see so far. So, I mean, technically this should be enough to like cause things to kind of start working here. So what we can do is the same trick here. We can just, pound if def under m under x64, hoping that that macro is defined. Else it's 32-bit. So we want to see just what's going to happen. I want to make sure there's no long casts. Okay, but that's okay. That's in the special code. Yeah, that's the only place. That's perfect. All right. So we're kind of like ready to take a look at what's going to happen. And maybe start like figuring out the details so we can just do this all extremely quickly. I mean, all we have to do, as I said, is kind of monitor that the addresses are adjusted right, and it's going to work. I mean, it's even simpler. There might be a little bit of trickiness to it, but it should be even simpler without all that stack management. It's just like a huge amount of that code went out the window. Like I said, it might be hard to generalize this in a way where you merge the code, at least up front. You want to finish the task and then think about just if it's worth trying to combine the code with macros or not. So the one thing we can kind of say about this is we know that this is going to need to do more work. It's going to need to do fix-ups. We're probably going to like make a little array of fix-ups or something, and then yeah, here's where we actually kind of get concerned, and we know like the details are going to come into play. And again, we need to make it work for release and debug builds and everything. And right now we have no idea what's going to happen. Okay, it doesn't have any arguments, is fine. Move ESI, ESP. So it's actually using the ESI register. Oh, it's checking the stack pointer because you're not allowed to change the ESI, and we don't, which is good. If we did, we'd have to push it on the stack or something. Have to save it somehow, or use self-modifying code to save it. That's always actually another option we could do. Is the first code could all be code to fix later code, but this still wouldn't work. We get this still strange relative addressing problem. Yeah. Okay, maybe you could do it with some loop tricks, really clever tricks where you're doing some kind of loop back so that you can reuse the IP address somehow that you've gotten only loaded once. There are some tricks to do stuff like that, where you keep incrementing that address a little bit to do the next fix up to do the next, and you keep. I don't think it's worth it. That's just novelty, but here that's not the point. Is to use like novel tricks. Um, okay, nice. It moves the address. It calls it. Okay. Yeah, we see it moves the ECX. Yeah, okay. Now here's where you see data segment, and this is where it's going to crash. I mean, did I call it or what? So, okay, we know that it's going to get to here and it's going to crash because FFFF1 should actually be pointing like here. It should be minus 15 bytes, but it's not. So what we're going to do is we're going to fix one of these instructions, and then we're going to fix all of these instructions. We just kind of want to make the concept first. It's a little slow to do it this way, but we can just say fix up. We'll just say fix up 1%. I think now we have to actually look at the list file to see where this fix up's occurring. Again, I think this, yeah, it's not going to be 1. Okay, so this one, oh, it is 1. 1, 1. Actually, we could do all of them. I mean, why not? We know anywhere there's an R here is a problem for us. So we can see all the fix-ups here. And we're just going to add the base address. That's it. All you do is add an address and you're done. So these are all relative codes. So, okay, so it starts here, and this is 1. Okay. That one's also 1. Fix up 2 is 1. Then this one will be fix up 3. It's also 1. The next one, though, is 2 and 2 and 2. Fix up 4%, 2%, because there's 2 bytes, or 2 groupings coming before. Fix up 5%, 2%. Okay, so we've done those fix-ups now. Again, this is going to make it start working a lot faster, right? Because all we have to do is then decide where some addresses are botched or where some code's botched. But actually, there's less self-modifying code here because this is like, you know, this C3. There's only a couple key places. There might be a couple others, but we'll look into all those right now. So, what else do we have here? And yeah, as far as I know, we're already using proper 32, 64-bit code everywhere. So the cool thing is we're going to fly through this here. So this is a 1 variant. I don't know if I should really be numbering them like this, but wait, that was 7. 1, 2, 3, 4, 5, 6, 7, yeah. 8, 9, 10. So this is a 2, a 1, ooh, and a 3. This isn't even one of them. Okay, I'm just making a mistake here. This is the one I was looking for. Fix up 8. Compare EX with D word pointer, it's 2. Then fix up 9. So we've got that one too. And then fix up 10 here. I think it's 1. No, it's 3. Wow. Okay. What else do we have? That was the 10th. Okay, we have 11, 12, 13. Wow, 13 fix-ups to do. All right, we decided not to just do a test one. We're just going to do them all at once because it's pretty easy. So the next is this load effective address. Which is a 2. Did I remember to put the comment tags in on all of them? Well, if I didn't, it won't compile. Yeah, I did though. So, okay, beautiful. Now we got like another here, I think. Yeah. So this is like fix up 11, and it's also a 2. No, fix up 12. And let's see. We'll do fix up 13. It's almost at the end. Yeah, this one. That one's already fixed up, so we're good to go here as long as it's a %2, which we are. So we're done. Actually, there's only 12 additional fix-ups. Okay, that's cool. So we actually are already done with that. And by the way, once we solve this, I mean, there's hardly anything left to do here. We're getting very close to just finishing this whole task all at once. The only thing will be like, did all the details end up working out like we expected or not? Because again, there's going to be little mistakes where adding one or forgetting to add one or something like that. Little offset computational mistakes, inevitable. Nothing to be done there. Okay. Wow. So we see the fix-ups now, and what I would say we should do is even like add like a little extra thing here and just put them in like a vector so we don't have to capture them all. I mean, I don't know, so we can generalize them. Again, they're constants already, so we could just, generalize them like maybe this or something. Because we don't have to do any computations because we already do that in the assembly language. All we need is to have them available so we can go through them. So that actually is kind of slick because this will be done at compile time. It's just like more constants. In fact, we don't even need those constants, but the compiler, we leave it to the compiler to figure that out and optimize them out. So the only problem we're going to get here is we actually have to define this over on the other side of things here too. And what we'll do is we'll just define them as an empty array. We'll just say, well, there are no fix-ups here. So we'll just define an empty array, and we can just use the size of the array to quickly enumerate that. This way we don't have to make a mess with this lambda stuff. We can just add fix-ups, and then we can just do them by, you know, a simple for loop. We're using I already, so j is less than, you know, the size of fix-ups over the size of, what is it, a size t? Okay, let's even be more accurate. We don't need to worry about the types. And now what we do is we use that fix-up to do this kind of increment. So actually that should do the job. This literally should be it. We should be done. Yeah, this one we actually use long, which seems like a mistake, but 64 and 32-bit both actually want it to be 32-bit, so I'm like, can you do about that? I want to regression test 64-bit, but I think we'll just hold off on it. Right now, I just want to see if this starts to work. Because if it does start to work, we can finish this, you know, in maybe 30 minutes, actually. It'd be a very short demo today. That's okay, though. Okay, so now we can look at the address and see what's going on here. So I see 520014, which is definitely wrong, because this is supposed to be referencing this address, 24. DB, I'm looking at that one. Yeah, this is definitely a mess. So what we can do is we can look in here and say, what was it originally supposed to be? It was supposed to be like minus 15. Oh, because the relative offsets were from the current instruction, but now we're just, we could do it that way, actually. I mean, that's not hard at all. I mean, well, it's almost just simpler to just do it relative to, you know, we not do this nonsense anymore, but just actually say the absolute from the start of the function offset. That actually would be probably fine. But we could also just fix it here if we want by saying that knowing that we want to be relative to this location. So yeah, I want to say I think this is right. Looks weird, but actually that is exactly, I think, what we want. But we'll see. Maybe I'm thinking about that wrong still. So now we see 21. Oh, that is just so close to being right, and it's just not right. So the base is going to be 23. And so if it subtracted 15, Because it needs to add 4. Okay, I mean, that actually is interesting. But then, because I see it needs to add, the address this offset would point to is here, is 30. So 30 minus 50, what? 30 minus, well, minus f is 21. Yeah, that's right. Strange, because we want it to be 24, right? So we see that this is what we want. We want 24. It's giving 21 here. This is ED. Is this also slightly off? Ever so slightly off, yeah. It's ED, but it should be 3 bytes more. But why 3 bytes? That's something we have to figure these things out. You can't just do guesswork with this. It has to make sense. So what on earth is this? This looks bad. So what happens is we're adding an extra 1 and we're not adding the 4. So it's like this combination of mistakes going on here. Ooh. Yeah, this is tricky. Oh, yeah. I'm of course I'm completely worried of yeah, how much of a mess this could be. Ooh. Yeah, that's kind of nasty. That is kind of nasty because we can be making easy mistakes here. Have to rebuild, recompute those offsets. I would obviously like to see this working quickly today. I don't want to spend a whole lot of time on this. I just want it to work. And I have a feeling that this is basically already, let's say about 80% of the work is done here. So now what we need to do is take a look at code again. Again, each time there's a mistake, we want to try to fix as many different mistakes as we can simultaneously. So we kind of expect this to be wrong still, but we don't particularly care because it should be. Oh. No, this is still bad. Wait, no, 20, 24. Now we just add size t. Yeah, okay, that's fine. So plus the size of the argument itself. Now, end of instruction is not necessarily always going to be there though. So this won't always work. Or will it? I mean, I don't know. If it does, it's just lucky. So big question, will it work? The only way is really to look at the list and see, is this relocation always the last thing? And yes, it is. Okay, so actually it will work. Turns out it will work. Oh, that's nice. But there's an assumption that the relocation comes last. So, okay, the nice thing is when you don't have to change the assembly, so that's always good. I just want to see if there's any 1+1s in here now. That one we know is necessary. It's just a bad comment. Okay, so no, that was just a bad comment. No big deal. All right, let's see if we actually have a little bit of traction on this. Yeah, okay, that's what we want to see. Now it's modifying 24, then it's going to modify F0. Yeah, this is exactly what we want to see. Nice. Yeah, perfect. So 1A007 is going to be the return address. So far, so good. So far, I have to say, now we're going to start measuring our percentage to just say how far we're done with this job. And we know that we're already starting to get near the 20% point. I'm going to get coffee. This is going to be a breeze now, I think. I have a feeling the Lambda might have a little bit of tricks to adding to the stack at the end, but these are just trivial little stack details that we can easily fix because they're not like some kind of like overall alignment type of thing that we have to maintain. We don't have to like balance anything out here now. Not dealing with alignment is really nice. I'm gonna just check it. So I'm getting mixed messages. Obviously, we know there's a 16-byte alignment requirement to be really interoperable with at least C code. It may be because of like variadic argument functions, but we know that there's going to be some issues with this type of alignment stuff. So the x86, as far as I know, is a 4-byte alignment. Yeah. Well, I'm getting mixed messages. Again, this is like something like going to Linux, you might get some issues with this. But again, our lambdas are very simple, so probably these details. I think it doesn't matter at all. I personally think it doesn't matter at all because we're not calling C library functions. We're basically just calling our own. Well, we are, using some STL functions, but they're all so simple. I highly doubt, even in the 64-bit side, we need to do something. But if we do need to do this, we know how. It's the same as the 64-bit strategy. We could align to 16 bytes if we need to. Again, the problem is that I'm getting difficulty figuring out the ABI is what they call it, the application, I think, application binary interface. And yeah, it's pretty unclear. And it may be very system specific. With 32-bit code, there was a lot more flexibility with how things worked than with 64-bit code. So let's see for now. Okay, F5, is it right? Looking at F5, it's perfect. So far all our fix-ups look good. A2 and 78, let's check them all. 78 looks wrong. A2 looks wrong. Okay, so we already see that there's some bugs here. How did those creep in? Because this should be +1 still. Oops. Oh, man. While we're at it, let's just check all the instruction addressing to make sure that it's all legit. Because we'll fast forward and we'll be done. We'll already be to the SCC part and we'll be, to the callbacks and all that. Or at least the Lambda functions and finding out what's going to go on. It's more fun to look at that stuff than this stuff is just silly. So let's see. 32-bit code. 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 32- Let's see some of these other addresses. 27. 27, it's wrong. Oh, no, it's not. 27. Wait. This should be 28. So this is a 1 plus 4. Ooh, this is a 1 plus 1 plus 4 plus 1. And I think we have that, a 1 plus 1 plus 4 plus 1. And this is a 1 plus 4. It's this move instruction that we're trying to change, which is definitely a 28. 1 plus 1 plus 4 plus 1. 7 bytes, yeah. And here is 5 bytes. Oh wait, this I said the relocation always had to be at the end, didn't I? And it's not going to be. Yeah. Look at this one. Oh, that's the wrong file. Yeah. It's this one. Yeah, this relocation is definitely messed up. Yeah, the C3 is coming here, so it won't know the end of the instruction. One option is just to add another one. Or subtract another one, basically, or not subtract one. So basically the strategy now is, since we're doing this fix-up, is to not use this. Just comment about it. But okay, so that's fixed. We understand why, too, because, again, as I said, the assumption was nothing came after, but it obviously did. Okay, so this is right, this is right, right. Okay, what are we doing at 59? Okay, fine, that's right, that's the counter. Here, that's the lambda. Here's the operator. Okay, that should work, but I'm not sure if the stack is... oh, there's no arguments, so that's fine, as long as we can do 4-byte alignment. Again, it's a lot of guesswork in knowing if these ABI details are even enforced in Windows. So I'd have to kind of really do some digging to figure out if that's the case. Okay, plus 1C. The way we can start looking at these kind of things is by looking at 1C here. Actually, this should be right. So 23 plus 1C is 33 3F, I think. Yeah, and so, I mean, again, that's right. F1 below link. Oh. Well, if this is EF, this is F0. Okay, this should be a 1 plus 1 compare instruction, and I think we just botched that one as well. Yeah. So it's not 5, it's 6. Okay, that's good. And it's good because at least we don't have to... like, once we clear out each of these instructions, I think we never have to deal with them ever again. That's the end of the story for them. So this is like another one. F0, but that's right, so it's right. B2, I'm pretty sure is wrong. Okay, EB3D. And why would it move it to B2 when it should be B0? Well, this is a 1 plus 1 plus 1 plus 4. So we take a look at that. 1 plus 1 plus 1 plus 4 is 7. So that's why it's off. So obviously it's just a miscomputation. Again, I changed too much of these too quickly. Okay, what's the next one? I don't know if this 3D is right. If I want to check it, we have to like look at B0 and add like 3D to it. Should be like FD or something. Okay, that also feels like it's wrong. It can't be. Can't be. This is such a simple computation. It's relative, and it should be relative, and we know this is too. I feel like it cannot be incorrect. So B, C, D, E. Oh, E, D is where I was supposed to look. Oops. Yeah, perfect. It should be here, actually. Yeah, sets the return and exits. So this should be right. There's not much left to do here. I feel like we've fixed a few bugs already. And again, we can kind of wait and see where it crashes, or we can like keep preemptively and logically looking at this. Some students messaging, so. All right, so I'm gonna. Whew. I'm gonna go get my coffee. Is what I'm gonna do. I feel like we're now probably. I'm gonna say 60%. My estimate is 60%, and I also estimate it won't take nearly as long. I think less than an hour to finish this, realistic even. And then it takes 8 hours, right? So that's usual programming jobs. So that's how life works. But no, I think we're getting close here, because I've already now made sure most of the fixed, most of the conceptual things going on are correct. Again, if we need alignment, we'll have to re-add some code to deal with that. But we know how to do it, so it's not like a particularly big deal type of thing. Oops, I don't want to do that again. Why? Oh no, I mean, the real challenge is to see how long does this take. And the faster, the better. Move on to something else in life. So, okay, F0, 8379. Are we happy with these addresses? Yeah, no, we're not. Oh, what? I just fixed this. This one's good. The 28's good. This is wrong. This is wrong. This has now gotten too big, actually. Yeah, what did I just do? I thought I fixed it. Oh, wait a second. I fixed it the wrong way. The other one is +1. We're changing the target and the source. Yeah, okay, so any others we want to verify? 59 is good. We don't need to verify that one anymore. Good. Again, some of the later offsets we don't know about yet, but that's okay. F0, F0, B0, 86. Let's check out 86. Good. Okay. What the is this? '86 is wrong because it should be loading the address after the call instruction, which is 85. So good, we caught another one. So yeah, I mean, at least we're in B0 is right. F0, I think we've already seen this one. It's right. Yeah. Any others? 86. Okay, we've said that one is wrong. 24. Is right. Again, the jumps can be EIP relative, of course. Jumps and calls and these types of things. Uh-oh. This is definitely wrong. Because we made it rip relative, and of course it's a fix-up now. Yep. Okay, so we will have to fix that one too. I mean, we're adding like a something as if it was rip relative, but what we should be adding is still the base pointer back into that. It's like a fix-up, a double fix-up. First we fix it up relative to the other node, then we fix it up relative to its base. So probably we'll just add that as another, actually it is the 13th fix-up. That's pretty cool because then we don't have to touch a whole lot of code to make that one work. 132 and 1FE. Oh, this is the next block. Yeah, I think that was it. I don't see much else wrong right now. Starting to look pretty promising here. So we saw that load effective address was off. So I'm going to go look at that one just to see what's going on with it. And so we see this is 6, so that's why it's off by 1. And that'll fix it. I'm just like hoping we can find, because again, the less we have to go through this process, the better. Hoping I can find some issues here. We're just going to stop it. We're going to, of course, regenerate the blueprint. We're going to add the other fix-up. Then we're starting to approach around probably even 80% coverage, because again, we know logically the only thing that we've changed is these fix-ups, and we've not done alignment for the stack. mainly because as far as I know, it's not required, but I'm not actually sure of that. As I say, I don't know. And it might be like a difference between Windows and Linux and that type of stuff, which, would be kind of annoying, but um, okay. This check same SCC offset is definitely one of the fix-ups. I think we're still going to be off by a little bit here. Probably we need to add, like, unfortunately, some value to that, but because is it at the end of the instruction? Yeah, it is. Actually, you know, let's see what happens. Let's see what happens. Let's just do the 64-bit one just for a fun regression. A little break. Uh-oh. Trying to think how to deal with that. Doesn't like me to do a 0-byte one. All right. I think I need to drink something besides coffee. I already finished the coffee. Actually, we're going to drink another coffee too. Feels like I'm on the verge here. And I think it's all I'm going to do for today. I don't think I'm going to do much else. Again, I'm kind of just completing the main key parts of the task here. The easiest thing to do obviously that's going to just corrupt stuff, so we don't want to do that. But what we could do is say, well, we don't need the fix-ups in 64-bit, so hope is this code still is right and still works. And again, that's what I'm saying. We just do a quick regression of all this. Because as I said, I changed one instruction, and it wouldn't matter unless there were 4 billion nodes in the graph, but I wanted to, just be absolutely sure. No. Okay. And then we don't touch this one again. We just kind of enjoy that it works. If it still works. Imagine if I broke it. That one was very difficult to get working. It's working fine. All right, I mean, I'm not even going to bother waiting for that. It's fine. All right. Back to the 32-bit world here. I forgot if I just copy and pasted the next code, which I think now has all correct offsets. Basically, we're to the point where I think it's going to call the Lambda now without crashing. And that means that we can start right there. It's only going to be the Lambda and the little SCC code that I think there's any chance now of a crash. So it's not a whole lot to debug. And as far as I say, the alignment I don't think is going to cause any issues right now, but technically, maybe in some, unknown circumstances, it could be important. Again, maybe if you're calling variadic arguments and stuff that definitely we're not doing, so it's just hard to say right now. My assumption now is A1 and 77 will be correct. Yes, they are. Okay, finally. Are we calling lambdas? Now, one thing we want to check is the stack pointer always. It's like our big problem at some points. So again, now we're not touching it as much, but we are expecting the lambda to do something. So it's at 2DC, which tells me that you see, the thing is Microsoft's not aligned it, I don't think, to 16 bytes ever. So I just don't know the details on, at least for Windows, if we need to do that. Maybe it's, some systems require such an alignment. And again, I don't know why that would matter, besides like maybe if you're doing some kind of variadic functions. Again, that's the other question. Does it even matter if you break the rule? Like, where would it matter? Again, it's something to do with maybe like where the function has to determine how many arguments there are. There might be some weird semantic tricks used there. Who knows? 59. Yeah, everything's good so far. So the question becomes, are we going to corrupt the stack, and is it going to make this call in return? So 2DC. Oh, ouch. Okay, so we're messing up the calling convention in the 32-bit world. Now, there's a variety of reasons this could happen. Now, I think it's a this call, so it should be in the CX register. This kind of gets fun to check out. Unfortunately, it's a big thing because we have several places where we're doing these types of calls, like 4 places. As I said, this is going to be like one of the key places we need to fix it. And yes, the stack alignment, if we need to fix it, would come into the same type of issue. It's nice not to have to fix it. As we can see, it simplifies the code. Beet and ginger juice, always good stuff. I'm getting more student comments. All right. So I want to see what happens when we call unsat. It's like the usual thing where you go into the disassembler, and we're going to start like saying what is going on here with a normal lambda call. So, okay, now, wow. So what we're seeing here, oh man. So unsat is a standard function. It takes the ECX. Oh. Again, we could actually do this same exact code pattern. We could do move EAX, ECX, but we don't want to do this, because if we do this, why is it EAX plus 8? Maybe on a release build it's EAX plus 4 and one of the functions isn't there. So we don't want to deal with like this kind of level of stuff. But we do see that it's putting it in the ECX. So it's in the ECX, has some like check for null pointer thing because we're in a debug build. Now it's using the pointer like this. So EAX plus 8. Now we want to see where it goes here. Okay, we get to this invoker. We get to 95C8EO. So we want to see that we put that address in the code. With 32-bit, we could simplify this code, actually. We could call the 32-bit address. I mean, there's stuff we're doing that's, like, basically unnecessary, but... That's interesting. But it's kind of annoying, too, so... Kind of annoying. Certainly, we want to use operator parentheses. We don't want to use another strategy. So another try. I don't think it's going to do anything, but just for the analysis purposes, we could try this. Should let me do that. We can just... Uh-oh. See if that should work. Again, it's probably the same thing though. Yeah, of course, it's exactly the same thing. This is, why does it have to be so tricky here? I have some instincts on how to proceed here, but this is obviously this is a blocker now because we can't even get to the SEC code unless this works. Obviously the captures are all being misaligned. Everything is just messed up here. I'm making coffee. Get ready for the long haul effort. Yeah, I need to get a coffee capsule. Okay, coffee capsule time. Yeah, one moment. You need to take a coffee break here. All right, back to action. Okay, so I don't know why it's using a different strategy here, especially in the debug build. Kind of interesting. And I'm worried if the release build is going to be any better than this. Trying to think if there's a way I could like cast this or something. There's gotta be some way to do this. It definitely starts with this ECX value, but the problem is it's not actually calling the operator parenthesis. Where is it? Oh, yeah, look at that. Why is it adding 4? To get to the data structure, I guess, yeah. Wow. See it talking about ABI and everything in these transition ABI. Wow. Hmm. Hmm. It's kind of tricky. All right. I'm I'm trying to think like how do we get that data structure out with being, still being as generic as possible. Target maybe? I mean, these are the same, so there's no point in having all this, but uh-oh. So what is target exactly? Yeah, it's a pointer. Why won't it let me do this? Is it private or something like that? Oh, I see. I don't think this is going to be right. Ah, I see. Oh, this is really going to be a hassle because probably what's going on here is it's this underscore target maybe that's being set. Yeah, I mean it's a mess of template classes here. You want it to be simple, but it's not basically. This is hmm. Well, it's still going to give me the same error. Yeah, can't deduce the type here. Where do we do the operator parenthesis? Again, we shouldn't obviously need the... I just want to get the number 4. That's what I'm looking for. Yeah, none of this is going to work. Oh, I guess we could actually... But I think this is actually going to give me the function pointer. So it's putting in the ESI at first. And now it's loading that address in here. Basically, I want to trick it into giving me a way to be able to use this kind of adjustment, because I guess it's not taking the same thing. I don't know what it wants to take here. Yeah, this doesn't look like it'll be so portable, even if I find some trick to get this to work. Yeah. Type info. These are protected members. I basically have to just kind of look into the details of this. These are all protected. Um, Impl, yeah. I have a feeling we're in some trouble getting this to do what we want it to do. I see. This is a full class now. Yeah. They've done this in a completely complicated way. I see why I'm not able to get this to work. So yeah. Uh, so the problem is we're calling apparently operator parenthesis on this underscore func underscore class. Maybe it's a base class. It's so complicated at this point. Class function, yeah. Get function impl, yeah, okay, so types. So it's deriving from another class, hence why those are protected. Private using my base. Again, the question is, how do we get the ability to call the base class? The interesting thing is, if we know that it's deriving from this, it's kind of internal stuff here, but if we know that it derives from this class, it may simply be that we need to do some kind of a cast. This is hidden from us. Oh yeah, it's in standard, huh? What am I doing? Yeah, we're gonna have to be really, really tricky to get around the fact that there's some kind of base class here. Um, Although, again, this is the details you have to deal with if you want to. Oh, what is it doing here? This is this is bizarre. My storage. Oh, it's telling us. Yeah, it's because it's deriving from a func class. My storage. Uh-oh. So it moves it from the ECX. Okay. Checks it's not 0. I see. Yeah, it's deleting this class. The real issues here seems to be the semantics of a base class and getting the correct ECX value for the base class. I mean, +4 or something like this seems logical, but okay, let's actually do this one again. There has to be some elegant, of course, general, like maybe semi-portable at least method, like a good basis for a portable method. Maybe you have to dig into the library a little, but FDF 404. So the question. Wait a second. I want to look at this unsat. To F4. One more. I missed something there, and it's not letting me get back out. So I want to look at this again because these pointers. This is what basically we have to get the address of one way or another. I think it's going to be this one. Func base void. Yeah. So it's this pointer here. Okay. I see. So apparently we don't want to call operator parentheses. We want to call underscore do call. But I don't know if we can access that either because it's private. Yeah. Oh, this is so tricky. So there's yet another base class in the mix here. Virtual, but again, oh, but it's public there. You got to be kidding! This is Nove table, Nove table. I don't even know what that is. That's like some weird decal split going on in there. This is so tricky. How do we get access to this func base? Because if we could call the func base do call, it would do the whole ECX job. I mean, we would end up fixing the whole problem. Okay, it's actually okay, coming from func impl. Yeah, that's I see. Yeah. It's weird because some kind of optimization must be going on here because it's like it never seems to call operator parentheses. I mean, one idea is to put a breakpoint on it and see if it'll let us. No, it doesn't. Oh, I'm in the release build right now. What if I was in the debug build? Oh, I didn't realize that. Wow. I mean, it might help. There we are. There we are. Because actually, if we learn anything here and in how this works, we may be able to. That's probably why I'm not getting this to work. This should work. I'm not doing the debug build. Okay, move ECX unsat. Call operator parentheses. I mean, oh. Oh, okay. This was I've been investigating a non-issue. Oh my gosh. This works just fine. As I said, it kind of did look suspicious. We got into the Lambda. Why do I think things aren't working? Of course, the problem is actually we didn't push an argument. It actually is. Oh, I can't believe it. So there is no problem. Good. That's good because we don't want this kind. Oh. Yeah, you said, well, I said it shouldn't take a long time. Well, it's taking a long time. Here we go, because I'm loading the argument into the DX register, and you don't do that, you push it. Ah, man, it makes me shake my head. Obviously, I know not to do stuff like that. Um, do these have any arguments? No, these are all void, so we don't need, it's only this one place. Ah. Oh, that's painful. That's absolutely painful. You just, what are we doing? EAX has, no, EX has nothing to do with any of this. Yeah, EAX will return the right value. EAX has the value we're going to call. Does it? Ooh, this looks really wrong. Something looks really wrong here. Not just that, but call racks. Oh yeah, this is the next call. I'm looking at the wrong one here. This is absolutely right. Okay, we can go back. Fixed a comment, but no. What we want to look at is this one. Yeah. Okay. So this one, actually, this one's fine. I mean, this is good. It's exactly the same logic using the CX. The only problem is we move EDX EAX. That's just totally wrong. We can just push that. And then because this is caller, I assume caller. Yeah, it's definitely going to be caller maintained stack. I think we just have to move the stack. We'll use LEA instructions. Something like this looks right to me. And now we're good. Now we're done. We rebuild, copy paste again, and that should be the end of this Lambda stuff. In fact, we should be 100% good on Lambdas, and which means we should be 90% now, and we should be able to finish this task. All right. Let's finish this. Let's finish this. I'm talking with my supervisor. He's attending a tutorial about FPGAs, which is an interesting topic. In fact, when you're doing this kind of stuff, I mean, can just imagine with an FPGA, you could actually potentially do some kind of self-modifying code. You know, a different way of thinking about the same type of problem than on an Intel processor. So it's kind of something I'm also interested in is the FPGA programming. Very, very close to the hardware level, so. And action. Or not action. Why on earth could that happen? Wow. Wait, I must have blundered something here. Oh, well, I just don't have. Oh, so it actually didn't crash? That's crazy. It didn't crash, but it corrupted the stack. Oh, wow. Oh, that's actually impressive. Oh, so we're actually maybe 90% of the way now. I don't know for sure, but okay, so what is the stack pointer? Because we know this is going to be our tricky one. And 9A4. So 9A4. And here it goes. We go on this little journey here through the code. We're going to assume this call is just going to work. So 9A4. Where's our stack pointer now at 9A0? 9A4. Um, yeah, I'm just shaking my head because I have no idea what just happened there. No idea. Oh, okay. So I do have an idea. Let's re-say that all. What's happening is the this call calling convention. What we need to do is look up the x86 calling convention and find out what the details of this call is. Obviously, okay, this call, either caller or callee cleanup. Oh man, this is where it gets weird. For GCC, it's cdecal, the caller cleans the stack. In Microsoft C, it's going to use standard call. And it is the callee that cleans the stack, not the caller. So we're not going to, certainly we're not going to add 4. That's out. This is tricky because, again, this is like very specific. So we don't need this instruction here. And what we can do instead of just doing all this stuff again, we can just find where it is. Now, I thought we popped the stack, so I don't know why the stack is changing on this call if we're popping the stack. Maybe I'm changing the stack pointer. We should never be touching it because we know that the lambda is going to clean up the stack. So it's interesting it didn't crash though. It just like bugged out on the stack being messed up. Okay. Why am I not finding what I want? Okay, I'm way too down in the code. Okay, it's here. So this 8D642404. Get rid of that instruction, and let's run it again and see what happens. So again, we're going to just monitor the stack. That's always a tricky issue with these things, is to make sure you're not messing it up. So BC, you have to really think in depth if you want to do this type of stuff. It's not a joke. This is... Okay, so it goes to B8 because we popped the stack. No, not yet. Now it's back to BC. So, okay, so the stack is like the same, which is good. We want it to be the same at this point. BC, all right, we're good. We're good to go now. We're good to go. It's going to call EAX, which is going to be the next node. Whoa. Whoa. Doesn't look good. So this is wrong. 7A and A4. Why? This is a 6 byte instruction and it's aligned at the end. Alright, I already fixed these on stack log +1. Let's see, 48, 8 plus 5 is 13, so 40. If I look at 40, that's wrong. What the heck? I mean, this should be 52. Minus 28. Alright, I'm just gonna validate these in the programmer. 52 minus 28 is 2a. I guess it's off by 1, yeah, 7a. No, it's off by more than 1. Yeah, it's modifying this stuff. BCC, yeah, it's modifying a bunch. It's way off here. It should be here, yeah. So this is, we can just figure out, it's off by 4 bytes. Some of these others aren't though, right? So, like 24, it's perfect. I'm, you know what I mean? It's just, I'm a bit stunned at what's going on here. But I have to think, there's some... Okay, maybe I should confirm this one works. Yeah, I don't understand how some of these are, so I don't need this anymore. We're done with lambdas. This is, it's now down to this some relative addressing stuff that I thought I had right, but apparently I didn't. So we have F3 here, F8. None of it's working. So $sign is representing, I guess, the current instruction. So, I mean, we should remember we want all of these relative to the end of the instruction, basically. So, relative to the end of the instruction would be 2e. So we have to add 2e to 25 and then just figure out why this isn't working. There's nothing else to do. Again, I'm overthinking this, but 2e plus 25 is 53. Which, by the way, is the exact right address. Oh, I'm wasting time. I'm wasting time. I forgot to rebuild. We can't just edit out a whole instruction. It changed all the offsets after it. Yeah, okay, that was debugging nonsense right there. I think I didn't do this again. Yeah, I should have done it. I should have realized we can't just edit the code like that. That was no wonder I'm sitting here like wondering what the heck's going on. As I say, this shouldn't be impossible at all. This should be relatively straightforward to get accomplished. Let's see what happens. Yeah, we're at that like last phase where it's it's tricky, but we've worked out all the details now. We've worked out a lot of the bugs. And yeah. Okay, again, it's like now it's still stack issues, but now we want to just go through the code and see how far it's getting. So far, we aren't getting nearly far enough because it was corrupting things. I'm assuming now this is fixed. Ooh, 76. Yeah, it is. Okay, it's perfect. This is what we want to see here. So we know, as we say, the lambda stuff should be satisfied by now. Now it's 8.4, so yeah, we've got a value on the stack. That's good news. Okay, it's going through its lambda. Perfect. Perfect. Oh, we jumped over that call. Okay, well, I don't know what would have happened there. 8.4 still on the stack. Oh, this was the first one, yeah, where it doesn't do anything. It just returns. Next one. So again, we're starting to get there now. We're really starting to get there. It's going to go through the second time. We see the stack is now 7C. Oh, now 80. Yeah, that's what I was going to say. I was surprised there's an extra 4 bytes, but no, it's not surprising. Now we're at the last function. Okay, this one we can just quickly go through and make sure that it returns cleanly. Because we know these ones are just going to return. Okay, whatever. Don't care. It should jump out of this. Okay. Now, is it on the stack? No, it won't be. .29e, is it loading? Yeah, it's loading the right address. It's pushing it. Should jump here. Yeah, it moves EAX. Moves ECX hopefully to the right return. Yeah, perfect. Okay, actually it's working. I mean, this is working. Yeah, this is working. Wait, I don't know where I am at. Okay, I think we're coming to the final component now. Yeah, this should be it. So it's 0 now. Things have actually updated in here for once. And now, C. Yeah, it's on the stack already. We know that one. Because it called other functions. Okay. Oh. What? All right, so I know where the problem is. We're not taking everything off the stack right now. And I know exactly, I think I deleted or I forgot to deal with this instruction. But we're close now. We're very close. Definitely. So let's deal with that soon. All right. All right, I think we've dealt with all the calling convention issues. I feel like the only thing we haven't dealt with is this one instruction here that's going to modify the. Oh, no. But technically, this should work. I feel like we have kind of looked at this. Okay, so we've still got the disassembly open. What we want to look at is this jump if greater than or equal and all this business. So probably we've just got an addressing error here where we're comparing to FC. FC, FC, I see it again. It should be up here as well. But obviously if it compares, yeah, it doesn't make any sense, does it? I'm not seeing right now why this would execute. Unless the lambda is not returning the value like I think. Yeah, maybe we're not done with the lambda. I thought we were, but this is weird. Okay, so this time we can start skipping. We don't need to go into all the other functions. We know they're getting on the stack. You know, most of this stuff's working. What we want to see is when it finishes a function call, what's happening right here. So it gets there. EAX is 0. Okay, that's good. That should be the lowling. Oh, okay, this could be the problem here. So now it's going to go back to a node that's already on the stack, should just return and load the AX. 3. Oh, wait, it is working. Oh, man. Don't know what I'm thinking right here. Okay, so we pop the AX now. Now we're going to start cleaning up the stack. 90C. All right. Probably these computations are not concise. And actually, we're going to watch them all right now. Actually, we should just put the breakpoint here. So, because if this stuff's concise, I think it's going to work 100%. 029E. Okay, 023D. 029E. Yeah, it's at the start. It found the base. 023D's right. That was the first maneuver, and we can simplify this stuff. It's not very difficult. Has nothing to do with any self-modifying. It's just some extra clarity instructions. So we're moving the EDX to that pointer value. I'm not worried about this either. And then it's going to add to the EAX D7. So we want to look at 314 and make sure that's the right address that I think it's going to be jumping to. And absolutely that is right. So we want to look at what ECX is here. It's a B9, so it's a move instruction. Again, we don't need all these extra moves in 32-bit world. We could simplify the code a little bit. But that's fine. It's correct. It should be a +1 offset. It increments the EAX. Okay, because obviously the EAX is pointing to a move instruction, and we want to actually modify what it's pointing to here. So it loads the ECX with the base of this one, 24. which is wrong, by the way. It should be 23. This one's wrong. Okay. Off by 1 here. This is easy to fix. Oh, this is good though. We're actually halfway through this last part. 95% right now. We're getting very close to actually having this working. There's no doubt. Should be 6. Oh man, it's the last fix-up. Okay, okay. Oh, yeah. Okay, we can actually just, like, hack this for the time being. Or we can just edit this. What is it? 7C705. Just work. Just work. You wish. Since we didn't change the byte counts, that should have been safe. Wait, did I change the wrong instruction? Whoa. Whoa there. I totally not thinking about that. Okay, careful. Extremely careful. This was the one? No. More careful. Man, I'm not even in the right file. This is sad. Here it is. So it's 8D0D. Subtract 1. Run it again and hope that it actually starts to work. Because honestly, I don't see what else is going to be wrong unless there's some final thing. Oh, wow. Yeah. Oh, how long did that take? All right, that was it. Finished. Finished in how many centuries here? Here. So well, it took 2 hours or something. Uh-oh. Okay, can we get the release build to work is another question, right? So now why is that 256 solutions? Whoa. Okay, so apparently it's not working. Apparently unsat is not working. Right? I mean, that looks like the unsat case. Okay, but we know why. But it's not corrupting the stack, And we know that there's just a miscomputation probably in the root of the current node. Mm-hmm. Oh, we know exactly why. Oh, this is easy. Okay, we'll do that one. Probably in a debug build, it's probably easier there. I'm just regression testing release to make sure I didn't screw this up. But we're basically done. Yeah. Okay. But before we jump for joy, let's fix this last bug. Which is just like some kind of offset miscalculation here. So what I'm going to do right now is I'm going to step in here. And what I'm going to do is actually step to the part where it's checking for unsat. So I'm actually not worried about this, frankly. I'm worried about the place where it stores the pointer to the root of the nodes and that kind of stuff. So we want to kind of look at this code right here after the jump. So what's EAX going to be? Is B30023. Now, is that right or not? It's absolutely right, so we're okay with that. In fact, that's what we like to see. Now, it's looking at 423, and that's where we think something's going wrong. So if we look at 423, yeah, it's off by 1 byte. Yeah. It's definitely off by 1 byte here. Last bug. Of course, this won't work if these can't be compared, right? It'll always think it's sat, and that would give me... But the great news is everything else works. It's like literally down to this one detail right here with this compare. So we look at this compare in the listing file, and we just fix it. I think we'll be able to understand why. So nodeadder setloc +1 looks good so far. $sign -5 looks like it's off by 1. Perfect. -6. I don't know if I should copy and paste because this is the final version now. So we get to the point where we can just look at this and we'll know that this is 3905 and F7 I think changed to F6, and yeah, that's how you do it. And now I think we're gonna get the right answers here. Cool. Yes, 3 hours today. Today was a 3-hour solution of the 32-bit world. So it wasn't that bad. But you see, today I was droning a little more, and I got stuck on a few red herrings where, what am I saying, red herrings? Not a red herring. A few tangents, basically, where I assumed something that wasn't true, and I just went off. I just went off into a deep, dark forest until I was able to undo being lost there. So obviously we're not going to run this in a debug build where STL is just horribly inefficient. But we do it in the release build, and now... Oh no, I didn't get this one. And now it's incredibly slow. We know it's about 7 seconds per iteration. Anyways, it works. I mean, I'm not pretty much being concerned that it's not going to work anymore. I'm sure that the 32-bit case is solved. So that wasn't too bad. This code is pretty bad, 32-bit code, because we keep moving immediate values into registers. Like, we don't need to move EAX and then jump EAX. We can just jump to the 32-bit location. Would be much better code. But this is actually very easy to fix. I could like fix some of them right now. This move EAX, call EX. We can make the 32-bit code just so much more compact. In fact, it kind of makes sense not to combine the code paths due to so many little differences here. But in a way, if we really super macro this, we can like everything call absolute address or RIP address. I mean, we could like try to generalize every one of these concepts. So, I mean, you can debate it either way. Anyways, I'm really pleased. This probably is going to be twice as slow. Seems like it, right? So, the memory usage goes way down here. You can see in the debugger here, the memory usage is dropped dramatically. Wow, it's slower in 32-bit world. For sure, it's slower across the board, but yeah, I mean, again, all of it. So I mean, nothing surprising here, but this is pretty nice. So again, that's it. So it's solved, and yeah, that was the 32-bit world, and all of its details. There it is, the standard call, whatever. Now I know going to Linux, there'll be more details, but again, we've filled in so much right now that if we want to go to Linux. Again, like, do you see how little conditional compilation is in here? It's almost nothing, like, for parsing the listing a tiny bit. And I think, like, one for the big blueprint, of course, because it's assembly code. But really, we didn't have to use conditional compilation at all. We just used proper C types for stuff. For the most part, that was enough. But when we go to Linux, we're going to find that there's some other problems. That's really another project for another day right now, because it will take some hours, probably take a full day at least, to get Linux. That's probably the next step though, because we do want to make this code really, really beautifully portable so that we can really be on top of this task. We can do it in the most common environments, in Windows and Linux. Those are the two best. I mean, if you have portable code that's 6432 Linux and Windows, it's pretty much flexible to do any type of research, any type of framework. It's very powerful. And so if I take this, I could also take it to like GCC on Windows, like using code blocks or something. And it's probably what I'm going to do at first, just to kind of probe a little, because GAS, the GNU assembler, is on Windows as well. And GAS supports not just the AT&T syntax, but I think it's the Intel syntax. There's two assembly syntaxes, and we don't want I like the syntax, the Intel syntax. I don't like the AT&T one, I think it is. So, and what's good is that Windows doesn't, or Microsoft doesn't support the AT&T syntax, but they support Intel. But the other one supports both. And so we'll just use that to our advantage. But there will still be conditional compilation, and details we'll need to fix there if we want to be able to use the assembly generator. Plus, parsing the listing file would probably be completely different. And all these things of emitting bytecode. And there'd just be a endless slew of little details in all that. That's basically all it is, though. It's just an endless slew of details. Will the C++ code work? This is also very good questions. Are the types correct? You know, did I use the right integers or long types or whatever in all the right places? This will be tricky, and debugging it there is going to be maybe a little bit more painful. Now, maybe there's a way to integrate in Visual Studio, the GCC. I think there is. And so, again, there's like a lot of options to investigate here, including like, you know, making CMake so you can choose, do you want to build it with GCC or Microsoft? And CMake would probably be a great way to go with this, because then it just becomes so easy. You could do it on Linux and it'll automatically choose GCC, and on Windows it can give you an option between the two, and you can just really have a flexible build process. And as I say, building anywhere, the assembly language is working anywhere. On Linux, we'll need to figure out not virtual alloc, but another call to allocate memory. But I'm sure it's pretty easy. I think, you know, we can look that up. I just say virtual alloc on Linux. It's easy as that. I see there's an mmap function to map pages of memory. Yeah, it's mmap. Okay, I mean, this is very easy. I think it's mmap and munmap, and there's an mprotect. So this will allow us to set executable read-write memory on Linux. This is so worthwhile doing, though, just to have the basis for this kind of a project. I mean, again, we could make a separate project file and not use CMake. There's all sorts of ways of doing this, but the next step is getting this to Linux, because this would complete a whole framework. And then if any more self-modifying code problems come up, we just use the same framework, and we can literally be portable 32, 64-bit. Yeah, we have to do all the details, but we have to do less of them. We can parse listing files, we can do this, we can do that. Whether we generate the ASM with gas or not might not matter, but you know why it will matter? Because the assembly will need to be slightly different for the Linux version, not because the machine code is different, but because the calling convention on Linux will be different, and so that's going to actually cause a problem. So if GCC is using cdecal, we'll actually have to use slightly different assembly code. So now, we could still generate it with Windows. We don't need to use gas, but we might as well parse a gas listing and just start getting really good tools for all environments, because I don't think it'll be too difficult. If it looks too difficult, then it might not be worth it, but I don't think so. I think it'll be a perfectly reasonable task. So one thing to note here is the Linux style. Again, when we're solving crucial key little details of the problem, we should put them, because that's the only non-portable code in here, basically. And the calling convention may not be portable. Again, will we be able to rip operator parentheses out? I think so. I think we won't have any issues with we should say G++, not GCC, but G++ will be able to probably allow all these things. And it probably is going to use the this call, but maybe with a slightly different semantics, only in the 32-bit. Again, we have to get it to work in Linux with 32 and 64-bit. You want to be comprehensive, and you want to know all these details. And then you have a powerful self-modifying code model. Can do anything anywhere. And you can interop with C. C is calling your self-modifying code model. Your self-modifying code model's calling lambdas in C. I mean, not just any C functions, but rather complicated to call ones, because you have to load a register. Not that complicated, but you do have to load a register and get some kind of operator that you can call. And yeah, I mean, it worked perfectly. Apparently, the compiler is generating code that's a little bit more to the point when it doesn't call operator parentheses. So we're finding that this actually, but it was still enough for me to figure out the correct way of doing this in a very generic sense. So we don't have to use any private, we don't have to use any details of like +4, +8. This is just totally generic solution. So far, I would actually say this is quite elegant. It's about as good as you're going to get in terms of trying to stay elegant for this. Okay, I guess it's giving me some warnings in here. Do we want to fix these? This one should be easy. I think the problem is we just forget to... you'd think assert false would be enough to get the compiler off your back, but apparently it's... no. I don't even know what this returns anymore. It's a vector, right? Yeah, it's a vector of ints. I mean, if we change this to an enum class, I think the problem is then we need to change. We need to scope all of these. It's yeah. Again, it's like it is what it is. We'd have to like go find all of these opcodes, which are all over the place, and put something colon, opcodes colon colon. They're saying that's cleaner. I kind of agree that maybe that is a better style these days than using kind of this global scoped enum. Hey, we can fix it. It's just the last task here. This is it. So. Does that work? Okay. Of course it does. Kind of an annoying thing to have to do. Should have done it like this the first time around, so you don't have to fiddle around with this. Just a silly change here. As I said, it was so annoying I didn't want to do it before, but I'm like, now, before moving on, it makes sense to kind of, before moving over to Linux, then you find out it doesn't work in Linux or something. No, it will. I'm sure Linux has a lot of great, or G++, I should say. Not. Well, it's my implication is Linux is the same as saying G++, even if it's not entirely the case because there's other compilers, but G++ is probably the most mainstream and the one I like to use. And it has the GNU assembler gas, and that's what is going to allow us to be cooking with gas over there. Of course, I'm missing the self-modifying instructions, and I'm making all the lines of code longer, so I'm not exactly pleased with this, but it is what it is. So we use the scope resolution operator to access those members. So there will be a few more here, and then we're done. What? Really? I got all of them. I guess I did. All right, so we're finished with all the warnings, and that's it. So we have a clean enough set of code right here. So obviously there's going to be a little bit of conditional compilation that we'll have to like, I think it's pound if win32 or something like that that's defined by Visual Studio. So we're going to clean that up. We're going to go to Linux, and that's the next step. So other than that, I'm going to say this is a mission accomplished for today. I'll see. Maybe I come back later and we'll start the Linux because, again, there's no reason to slow down here. Might as well just carry on and get the whole thing done because then we can just be so multi-platform, multi-architecture. And even if we needed to go to Android or somewhere else, eventually we could figure some way or another out to do it because we'd have looked at a lot of concepts involved in doing it. Yes, of course, it does depend on the architecture heavily and the compiler and all sorts of things, but at the end of the day, once you've looked at enough concepts, you at least know what to look at to see if the job is possible there, based on, does the processor allow this, or how you can trick the processor, if it, doesn't have proper instructions to load 64-bit registers with one instruction. Maybe you have to use two instructions. Waves, we could do that here as well. So there's always workarounds. Usually they become slower and less elegant. And yeah, I'd like to do more algorithms. I'd like to do some, even some parallel algorithms. I have a bunch of ideas, but before I do it, I think we should go to Linux first. So, okay, thank you so much, and that's the end of this stream, and we will be back next time with some kind of Linux improvement, and before we go on to the next task, which will no longer be 2SAT, it'll be something else, because there's not much more to say about 2SAT unless we're going to try to solve the topological sort issue, or maybe we want to do more performance measurement details, and we could do that right over in Visual Studio. So, and I would like to link GCC into Visual Studio. I think there's a way to do that in the, not extensions, but actually, probably I already have it here. Probably we can just go to the properties somewhere, and there's a way to tell it, hey, I want to use the platform tool set. Yeah. Oh, look I can use LLVM Clang. That's cool. So I mean, yeah, I don't know what the options are here, and we're using what, C++ 14. So okay, so that's all, and we'll be back next time with more stuff, mainly Linux. That's the last major task, and it could take a day, but maybe it won't. Maybe it'll be much faster. It just depends on some of the details there. I hope it doesn't. I hope it's fast. But the other thing is, as I say, the maybe performance tuning, because this code is reusable. At the same time, the strongly connected component code for the other 2SAT, other models, is probably fine-tunable. And as well, we could even write a more optimized version. And I think we should do some of these tasks as well. We shouldn't just like say that this, just because I did one model, is actually isn't trying to short circuit and isn't efficient as an strongly, well, is efficient as a 2SAT as you can do, because it does do the checks in the reverse topological order, maybe too late in the game there. However, there might be consequences of doing it, not doing it to its completion, in that if we want to find the next solution. So there's going to be this trade-off, and we'll look at the trade-off first with just normal C code. We'll go way back to the normal C code, analyze the trade-offs, and then see what's the best way to quickly decide SAT or unsat, which obviously use short circuit, but then also to enumerate or count solutions and what's the best solution there. And then we could kind of come up with something there. So, okay, take care. Thank you.